Our next section is 8.6, Integration Strategies. In the previous 5 sections, we introduced various methods for evaluating integrals, though always in the context of learning a specific technique. For instance, in section 8.3, we focused on integrals involving trig functions. In this section, the chief goal is to illustrate how to attack a generic integration problem when the appropriate method is not obvious. As a starting point, we assume that you know all the integrals listed in Table 1 below, and that you're familiar with the reduction formulas presented in sections 8.2 and 8.3 earlier in this chapter. In addition, you should know the formulas from Calculus 1 that involve hyperbolic functions, and these are up here to the right. In what follows, we offer a collection of strategies to use when confronted with an unfamiliar integral, illustrated with brief examples. Rewrite the integrand. Several techniques can be used to transform an integrand. We can split up fractions. We can use long division or trig identities. We can complete the square in an integrand that includes a quadratic function, perform algebraic manipulations such as multiplying numerator and denominator by the same expression, and cancel common factors. So let's look at an example. Example number 1, evaluate sine x plus 1 over cosine squared dx. Here, if we split the fraction and use trig identities to rewrite the integral as the sum of two integrals. So note we have sine x over cosine squared x plus 1 over cosine squared x. And then if we split sine x into a product of two fractions, we get sine x over cosine x times 1 over cosine x. Okay, well, 1 over cosine x is secant, sine over cosine is tangent, these are trig identities, and plus 1 over cosine squared is secant squared. So we can see here that we can write these in terms of very simple functions that we can be integrated using what we saw in table 8.1. As a general rule, if an integrand contains the function and its derivative, the substitution u equals f of x often results in an easier integral. When attempting to evaluate an integral using the substitution method, it is important to understand that there's no list or rules one must follow. Any substitution is fair game. On occasion, a creative substitution does the trick. Evaluate the integral of x squared divided by the square root of 4 minus x to the 6th dx. Expressing the denominator of the integrand as the square root of 4 minus x cubed squared looks promising, particularly because a constant multiple of the derivative x cubed appears in the numerator. Therefore, we try the substitution u equals x cubed. If we rewrite the integrand like this, as it just stated, changing x to the 6th to x cubed squared, and set u equal to x cubed, well, du then equals 3x squared and is a simple substitution. And then we can see here from our table 8.1, the integral of du over the square root of 4 minus u squared is a standard integral that we went through in previous sections in chapter 8. Recognize common patterns. Integrate the product of two functions often calls for integration by parts, which we did in section 8.2, particularly if the factors of the product are a polynomial and a transcendental function, log, exponent, trig, or inverse trig function. In some cases, integration by parts is successful when the integrand is a single function. Powers and products of sine and cosine, tangent and secant, or cotangent and cosecant are integrated using identities, reduction formulas, or the substitutions given in tables 8.2 and 8.3 from section 8.3 that we recently covered. Integrals containing the expression a squared minus x squared, a squared plus x squared, or x squared minus a squared may yield to trigonometric substitution. Use the substitutions given in table 8.4 from section 8.4 to tackle such integrals, but don't overlook a simpler solution if it's available. And the last one, use partial fraction decomposition, what we just did in the previous section 8.5, to integrate rational functions. Remember to first cancel the common factors and to apply long division if the rational function is not proper. So let's look at example 3, which is asking you just to think about a technique of integration that would work for them. This doesn't just mean for you to suggest, okay, this is integration by parts, but to show the kind of steps that you would do to set up the integrand or to start the process. So let's look at the first one, the integral of 4 minus 3x squared over the quantity of x times x squared minus 4 dx. Here we can see that we have a rational function whose denominator factors easily, so partial fraction decomposition is an obvious choice. In the denominator we would have x and x plus 2 and x minus 2, so we could figure that out. However, it's worth considering other options that may save time. If we expand the denominator, we recognize the integral admits an almost perfect u substitution. If you multiply through the denominator, we get x cubed minus 4x, and you can see that the derivative here is 3x squared minus 4, which is just the opposite of 4 minus 3x squared. So we could pull the negative out in front of the integral and do a simple substitution here. So while sometimes we see patterns, it may help us to kind of look at things from a couple different perspectives. And I think that's really what this example is all about. So now let's look at part B, the integral of x times e raised to the power of the square root of 1 plus x squared dx. There's a couple things that I could see here. We have the a squared plus x squared, so we might want to do some trigonometric substitution. We also might want to do, this looks like some of the problems that we did in integration by parts. The integrand suggests several techniques. The substitution, as I just mentioned, u equals 1 plus x squared, looks promising. Oh, that's just a simple substitution. I didn't even mention that, sorry. If we make u equal 1 plus x squared, well, du equals 2x, and so that sort of looks like it could work. And then you'd have this integral here. But then it gets a little more complicated if we'd have to do a substitution followed by integration by parts. So that didn't really work out so well. Given that the integrand is a product of two functions, we might try integration by parts as a first step. We leave it to the reader to conclude that this path isn't fruitful either. Finally, the presence of 1 plus x squared in the integrand suggests the substitution of x equals tangent theta, which leads to the following integral. If x equals tangent theta, then remember dx would equal secant squared theta d theta. So we have x, so that's tangent theta, e to the square root of 1 plus, again, x squared would be tangent squared theta, and then dx equals secant squared theta d theta. We just went through all of these, I believe, in section 8.3 or 8.4. 1 plus tangent squared is secant squared. So then we can do a substitution here where we let u equal secant theta, and then du would equal secant theta tangent theta. And we actually did this integral, this final one, u e to the u, in example 1 from section 8.2, using integration by parts. So let's look at the last example, part C. the integral of the natural log of 1 plus x squared. Again, we have something that looks like the form of a squared plus x squared, which might give us a possible technique, which is what the first sentence here is. We could make x equal tangent, which yields the integral of the natural log of secant squared theta. And then if we use integration by parts in this new integral, it eventually leads to the answer. But this is suggesting that it's more efficient to use integration by parts from the beginning. And so we try the following choices for u and dv. We make u equal the natural log of 1 plus x squared, and then dx equal dv. And so you see the table version here. The derivative of this is the derivative of the natural log is the derivative of the argument over the argument. And of course the integral of dx is simply x. So we get this integral here. This would equal x times the natural log of 1 plus x squared, that's the diagonal, minus 2 times the integral of x squared over 1 plus x squared. And this new integral is handled with long division followed by a routine integration. And there again you can see some additional problems suggested that are related to these. Here's some great advice for calculus. Just keep swimming. The examples that we just looked at from example 3 bring to light two important ideas. The first one is to recognize that more than one technique will work for a given integral. Typically, when you do this, one technique is usually easier or more efficient than the others, but determining which one is not always easy. So you may have to do what we call the trial and error method. To determine which choice is best, you may need to carry out the first few steps of a different technique, several different techniques, in order to recognize the best approach. And also be persistent. Be prepared to experience dead ends. Just keep swimming when attempting to evaluate an integral. For example, let's look again at the very first example from this chapter where we integrated the sine x plus 1 over cosine squared x dx. Instead of splitting the fraction as we did when we worked through example 1, which was a really simple analysis and then really simple integral to solve, here we're going to split the fraction using the Pythagorean identity that cosine squared, the denominator in the original, equals 1 minus sine squared. Well, when we do that, we can see this is the difference of perfect squares, so we can factor the denominator into 1 plus sine x and 1 minus sine x. And, addition is commutative, so 1 plus sine x is the same as sine x plus 1, and so these cancel out. Typically, when we see this, it makes us excited because it looks like we've simplified the integrand, and we have. Indeed, we've done everything correct here, but what we're integrating now isn't really that simple to integrate, and so we're going to have to try something else. Even though we did simplify the original integrand, this just didn't work out as far as figuring out a method or technique to solve this last integrand that worked like what we did in example 1. So again, keep swimming, try things, and try not to get frustrated. Try to think of it as a learning process.